Hey guys, welcome back to my channel. Today, let's talk about the second episode of hypothesis testing, significance level. The first episode is about how do we understand hypothesis, right? This term hypothesis, and today's video, which is the second episode of the video series about hypothesis testing, significance level. I will mainly use one sample test hypothesis as an example. To talk about this, how do we understand level of significance, or why do we call it a significance level, aka the probability of committing type 1 error. Okay, and yeah, so without further ado, let's dive in. Let's talk about significance level. Okay, significance level, or level of significance. We just use alpha to denote the level of significance. This video we mainly talk about why do we call it the level of significance, or why is it called significance level. Okay, so this significance level use this lowercase Greek letter alpha to denote. So alpha significance level, aka as known as the probability of committing a type 1 error. I talked about type 1, type 2 error, the differences in relationship in the videos before. Okay, just check out my video about type 1, type 2 errors. Okay, the significance level is the probability of committing a type 1 error. A type 1 error basically means you reject a true null hypothesis. Today's video, we mainly talk about one sample test hypothesis. One sample test hypothesis. There will be two case scenarios. So case number one, we assume we have a two-tailed test. So two-tailed hypothesis test. Again, this is one sample test hypothesis. Okay. So now let's suppose we have a null hypothesis mu equals 85. And alternative one is mu is not equal to 85. This is a two-tailed test. To know is one-tailed or two-tailed test, we basically look at the alternative hypothesis, H sub 1. If there's no direction specified in this alternative hypothesis, it will be two-tailed test. That means you're not only interested in whether population mean is significantly greater than 85, but also interested in whether population mean is significantly lower than 85. Okay, one-tail test, let me write here, one-tail test. So null hypothesis could be, right, alternative one. This video is actually a continuation of the video series about hypothesis testing, or one sample test hypothesis and two sample test hypothesis. So here we focus on one sample, and we said that from the episode 1, right, hypothesis. So we always use alternative hypothesis, H sub 1, to reflect our research question. For example, our question is, I'm interested in whether population mean is greater than 85. So now this is mu greater than 85. And then accordingly, a null hypothesis will be mu less than or equal to 85. Okay, so this will be one-tailed test, the case scenario number 1 and this case scenario number 2. One tail, that means you're only interested in whether population mean is greater than 85. You're only interested in one tail of the normal distribution. Okay, so now let's just focus on two-tailed test first. We want to know whether population mean is 85. So what we do is of course, we don't have population data, right? What we can do is rely on the sample data. Let's suppose it's a large sample. So we take a sample N, suppose it's large enough, and we can compute a sample mean, maybe 90. And of course, we can have a sample standard deviation, right? So that's maybe is 6. So let's suppose we don't know sample standard deviation. Okay, so this is, you have the sample data like this, 1, 2, 3, all the way to 36, and X, the variable, okay, the variable is X, thing you're interested in, take on different values, so like this. This is your sample data. You always know your sample size. You can always compute your sample mean and also sample standard deviation, right? So this average of this sample maybe is 90. So because large sample, we use the most important conclusion in statistics and also all of mathematics is central limit theorem, right? Central limit theorem. Central limit theorem says when n is large enough, sample mean x bar follows normal distribution. Right? Sample mean follows normal distribution. And with the mean, population mean mu. So this is the expected value x bar equals population mean. So what is the value of this population mean? So that's one of the key points is we always assume this null hypothesis is true. So we always assume this is a true null hypothesis, and we look at how likely we observe the particular sample mean a specific value, for example 90. So we assume this population mean is 85. So that's population mean is 85. So that's, we just use this hypothesized population mean 85 as our true population mean. We just look at how likely or what the probability that we observe value x bar equals the computed value x bar 90. Okay, so if 90, let me just use this color. So if 90 is somewhere here, maybe it's very close to 85, or maybe 90 is somewhere here, a little bit farther away from 85. I want to know, how likely is unlikely, or under what condition can we say the difference between the sample mean 90 and hypothesized population mean 85 is significant. We just want to know if this difference between hypothesized population mean 85 and the sample mean 90 is significant, or if this difference is significant, whether the difference is statistically significant. So that's why we need a standard. We need a significance level. So significance level is always a probability because this is a continuous probability distribution. This is normal distribution. So in social science, by default we're using 5% significance level. Let's suppose this is a 5%. So 5%, right? Let's suppose this is 5%. 5% in this case scenario, two-tail test. That means two-tail, right? Again, you're not only interested in whether the population mean is significantly greater than 85, maybe somewhere here, or significantly less than 85 somewhere here. So that means the two areas are supposed to be symmetrical, right? The two areas add up equals 5%. So if this is a two-tailed test, so that means the 5% significance level just evenly distributed on those two tails. So this area will be 2.5%, right? This area will be 2.5%. So that means that gives you this this 5% significance level just to give you this condition under which the difference between the sample mean and hypothesized population mean is statistically significant. So if 90 is fall in this area, is anywhere in this white area, anywhere within this white area, right? So if 90 is fall in here, we say because it's in this 2.5%, right? Because this fall in this 5% significance level area, and we see the difference between 90 and this 85 is statistically significant. The difference, okay, let me write this way. The difference between hypothesized population mean and the computed sample mean is statistically significant. The difference is statistically significant. Okay. Or if the value somewhere here maybe is 60, right? So it's falling this area, we call this difference. We say this difference between this value x bar 60 and hypothesized mean population mean 85 is statistically significant. Right? But if 90s fall somewhere here, 90 is here, if this value falls outside of this 5% significance area, and then with the difference between hypothesized population mean and the computed sample mean is not statistically significant, or the difference is just due to chance. Okay, so it's not statistically significant. So when the difference is statistically significant, or when the sample mean falls in this rejection area, not rejection, fall this 5% area, we can make this conclusion saying that if, let me just write here, if no hypothesis is correct, is true, i.e. the population mean is 85. So if this is true, because we assume this is true, right? That's why we need a equal sign and null hypothesis, because we need a value to plug into our formula, which I will show you later. Now let's complete this sentence. If a null hypothesis is correct, is true, i.e. mu is 85, and then the probability that you observe, the probability that x bar, right, is as extreme as or more extreme than the computed x bar is less than 5%, or the probability that you observe 90. 90 is greater than 85, so more extreme than 90, that will be even greater than 90. So as extreme as or more extreme than this 90, right, is small. In this case, fall in this 2.5%, right? You can say is less than 5%, or even less than 2.5%, right? So what does this mean? That means if the null hypothesis is true, it's only less than 5% chance you randomly select a sample and get a sample mean 90, right? This large. Right, so if this is a true population mean, it's very unlikely, less than 5% chance, even less than 2.5% chance that you randomly select sample and observe the sample mean this large, right, as large as 90 or even greater than 90. Okay, so if you have sample mean, take a different sample, compute sample mean 60. So now suppose 60 fall in this rejection area, and then you can say, if null hypothesis is true, i.e. the hypothesized population mean is really 85, and the probability that you observe sample mean as extreme as or more extreme than 60, more extreme, that means even less than 60, because 60 is already to the left of population mean 85. So as extreme as or more extreme than 60 means even less than, right? Less than or equal to 60, and this is less than 5%. Okay, so that means if the population mean is really 85, it's less than 5% chance you randomly select sample and observe the sample mean 60, this small. Okay, and that means, or that indicate the null hypothesis is not supported by the sample mean. In other words, let me show you this. Let me show you here. So if null hypothesis is true, or is true, okay, this check mark is true, that means this is a population, okay, I1 all the way to n, and x1 all the way to xn. Now suppose the population mean is really 85, and then you randomly select a sample, and sample contain this many observations, and the sample mean is very, very unlikely the sample mean is 90, this large, or is 60, this small. You turn this logic around. So that means if you pick a sample and you compute the sample mean 90, this large, it's more likely that this sample is coming from a population with a mean greater than 85. Okay, so, or if you take a sample and compute the sample mean 60, and this 60 sample mean suggests that it's more likely this sample is coming from a population with the population mean different from 85, or maybe less than 85. Okay, so either greater or less, that means the different from 85. Okay, so the hypothesis testing, the logical hypothesis testing is just we assume the null hypothesis is true, is correct, and then we calculate the probability that it will observe the sample mean as extreme as or more extreme than the computed sample mean. If this probability is small, right? But how do we know it's small or large? And we need a level, we need a significance level. If this is less than significance level, and then we say it's very unlikely, right, to observe this value, this sample mean. So that means this sample data 90 does not support the population mean is 85. Okay, but if this is greater than 5%, 90 somewhere here or 60 somewhere here, and then we say the sample data support the population mean is 85. Okay, that means we fail to reject null. So if this is true, right, we say we reject null hypothesis. Right? If null hypothesis is true, it's very unlikely we'll observe the sample mean this large or even more extreme than this value. If the null hypothesis is true, it's very unlikely, less than 5% chance, right? Less than significance level that we'll observe the sample mean this small. So we can conclude that the sample data does not support the population mean is 85. So the null can be rejected. Okay, and same thing for a one-tailed test. Okay, to reduce the length of today's video, I'll talk about one-tailed test in the next episode, so stay tuned. For the one-tailed test, I'll update you very soon, so stay tuned. Any questions, please let me know. And thank you so much for watching. Hope you find this helpful, and see you next time. Bye.